Hello everyone. Today we are going to discuss one of the most important theory in coordination chemistry, that is the crystal field theory. Earlier we have studied Werner's theory and valence bond theory. This theory, the crystal field theory, is more advanced than both those theories. This theory was proposed by Hans Bethe in 1929 and it was later modified in 1935 by J.H. Van Wyck. According to pure crystal field theory, it assumes that the only interaction between metal ion and ligand is an electrostatic or ionic one, the ligand being regarded as point charges. In pure crystal field theory, that is the only interaction, that's the important thing, the only interaction between metal ion and ligand is an electrostatic or ionic one. Later we will study about the ligand field theory. This is the crystal field theory. Later on we will study about the ligand field theory, where there is uh, ionic interaction as well as covalent interactions. Covalent character will be incorporated in that theory. And the difference between crystal field theory and ligand field theory is that the crystal field theory only assumes that the metal and ligand has electrostatic or ionic interactions. We can see the metal. It has a positive charge and the ligand either it is point charge or point dipole. It is Cl minus or Br minus are examples, and for point dipoles ligands such as H2O or NH3 which is having lone pairs durationate are the examples, and the interactions are purely ionic or electrostatic in nature. And there are many postulates of crystal field theory. This theory considers a complex as a combination of central metal ions surrounded by ions or molecules called as ligand. And there is the metal, and surrounding the metal there are ions or molecules, and we call them as ligand. And this ligand, as we already discussed, can be point charges like Cl minus or Br minus, or as point dipoles like H2O or NH3, etc. And the second postulate saying that we know the metals, we are taking the d block elements mainly, and the d orbitals of the central metal have same energy, and they are said to be degenerate. That is, they are all having the same energy. That is, there are 5d orbitals and they all are degenerate. That is, they all are having same energy, and the degeneracy is destroyed by the approach of the ligand during the formation of a complex. And when the complex is formed, either it can have a octahedral form, octahedral geometry, tetrahedral, square planar, and so on. And during this time, the degeneracy is destroyed and the d orbitals are split into different energy levels. And when we come to the interactions, as we already discussed, the bonding between the metal cation and the ligand arises due to the electrostatic attraction between the nucleus of the metal cation and the partial negative charge present in the ligands. That is, we are discussing about an attractive interaction, as we already said, and the bond between the metal and ligand are purely ionic in nature. And there is a second interaction, that is a repulsive interaction. The interaction between the electrons of the metal and those of the ligands is entirely repulsive in nature. And these repulsive forces are responsible for the splitting of the orbitals of the metal cation. And to summarize the two interactions, there is the attractive interaction, which is ionic in nature, and the repulsive interaction is also there, and this repulsive interaction is the cause of crystal field splitting. That is the splitting of d orbital, degenerate d orbitals into different levels. That is the crystal field splitting. The splitting of d orbitals, that is the crystal field splitting, and its consequences are considered as the backbone or heart of crystal field theory. It's one of the most important thing. The splitting of d orbitals and its consequences are considered as the backbone or heart of crystal field theory. And to have a fine grip on crystal field theory, one has to have a clear idea on the shape and distribution of d orbitals in shape. That we all know there are 5d orbitals: dxy, dxz, dyz, dx square minus y square, and dz square. And we should have a clear idea on the shape and how these d orbitals are oriented or distributed in the space. Or no, the 5d orbitals. And these 5d orbitals can be divided into two. First three orbitals, that is the dxy, dxz, and dyz orbitals. They are all considered as orbitals in between the axis. We all know the Cartesian coordinates, and if we consider two axes, a two-dimensional representation, x-axis and y-axis, if the lobes of these d orbitals are in between these axes, x and y axis, we call this as the dxy. And if the lobes is between y and z, we call this as dyz. And the lobe is between dx and z, we call it as dxz. That is, these three orbitals are orbitals that lie in between the axes. And the rest of the two, dz square and dx square minus y square, these two are orbitals which lie along the axis. We can see the z orbital, and there is a donut-like shape in the center where the electrons are oriented in the xy plane. Here, the distribution is in the xy plane. The dz square orbital is actually a representation of dz square minus y square and dz square minus x square. We say it as d 2z square minus x square minus y square, and we represent shorthand as dz square. Actually, this is the original representation. This was asked in several postgraduate entrance examinations. So note this down. So we say that the 5d orbitals are divided into two, that is, orbitals along the axis and orbitals in between the axis. And we name them as T2G. The orbitals in between the axis are called collectively known as T2G, and the orbitals along the axis are collectively known as EG. So dxy, dxz, and dyz constitutes T2G orbitals. dxy, dxz, and dyz are T2G orbitals, and orbitals in between along the axis, that is dz square and dx square minus y square, is considered as EG orbitals. And this T means triply degenerate and E means doubly degenerate. That's we have already discussed. Degenerate means having the same energy. So the E and E comes from the group theoretical symmetry element, that is the I center of inversion. It's for octahedral complexes. For tetrahedral complexes, we only say just T2 and E because it's like the center of inversion I.